Now let's talk about how waves interact with matter and with each other. We'll start with a reflection. A reflection is when a wave hits a surface and then bounces off of it. The law of reflection tells us that the wave will always bounce off at the same angle that it hit the surface. This is assuming that the surface is very flat and smooth. If the surface is rough or craggy, then the waves, may be bounced off at many different angles. But take, for example, the surface of this very smooth, still lake. You can see the reflections from the tops of the mountains that are coming down and then bouncing up to the camera, and they bounce off at exactly the same angle. So the tips of the mountains and the reflection seem to be exactly the same distance below the water surface as the actual tips of the mountains above the reflection. The reflected mountains seem to have the same height as the actual mountains, and that's because the reflections are bouncing off of the surface of the water at the same angle that they hit it. Sonar is a technology used by people, but also used by animals like bats and whales, and it's actually an acronym. It stands for Sound, Navigation, and Ranging. It's basically a type of sound wave that is too intense, too high frequency for humans to hear, but you can send it out and it'll bounce off of objects and come back to you. And if you know how fast sound is traveling in the material that you're in, you can calculate how far away the thing is that the sound wave hit. Use this in things like submarines and boats to image objects that are underwater that we can't directly see. But it's also used by animals like bats, whales, and dolphins, and they don't mentally do the calculation. When they send out a little ping, they don't have time to go into their brain and say, okay, the distance is equal to speed divided by time. They can't do that, okay? Or speed times time, excuse me. They can't do that. They sort of mentally do it automatically. Next up, refraction. Now, refraction, be careful, it sounds like reflection, but it's not the same. It has an R in it. Refraction is when light passes from one material to another and it changes its direction. If you've ever seen a pencil in a glass of water and it looks like the pencil is broken, or it doesn't have to be a pencil, it could be a straw or anything else that's sitting in a glass of water, and it looks like it's broken or bent, that's because of refraction. It's because the light that bounces off of the pencil or the straw or whatever comes out of the glass of water and changes its direction. So to your eye, it looks like the pencil is in a different location. If you've never seen this before, I strongly encourage you to try it. Go get a clear glass, pour some water into it, and then put something. It doesn't have to be a pencil, it could be any solid object, but put a solid object into there and observe how it looks like the solid object is bent or broken because of the refraction. Diffraction, and I apologize, I know these words all sound kind of similar. Diffraction is when a wave passes around the edge of an obstacle and gets bent as a result of passing around that wave. So for example, here you have these lines represent what we call wave fronts. If you imagine seeing the wave from the side with the crests and troughs, you can think of these lines as representing the crests or the troughs. It really doesn't matter. Anyway, they're striking this barrier, there's a small opening, and as they pass through and around the edges of the opening, they get bent outward, so that the wave, as it passes through the opening, gets rounded outwards and it spreads out, so that people over here, if this was, say, a sound wave, people over here would be able to hear the sound wave, even though technically they should have been blocked by this barrier. Here's a picture of ocean waves diffracting around the opening between two large bodies of rock. You can see that the ocean waves are coming in this direction. You can sort of make out the crests of the waves coming in parallel to the shore. And as they pass through this little gap, then the ocean waves spread out in this circular ring shape, traveling outward and away from the edges of the gap. That's diffraction with a D. And finally, interference. Interference is when two or more waves arrive at the same place at the same time. Now, constructive interference is going to be when a crest meets a crest or a trough meets a trough, and the amplitudes of the two waves will add together and make a bigger amplitude than either wave had by themselves. Destructive interference is when the crest of one wave meets the trough of another wave and they cancel each other out, so they make a wave with a smaller amplitude. A standing wave is when a wave interferes with its own reflection. So in this top animation, we have constructive interference. Just to make things simple, I've only shown the crest of one wave meeting the crest of another wave. Because they're both crests, when they meet, they temporarily build up into a much taller wave. Here we have destructive interference. We have the crest meeting the trough. And when they meet each other for just a split second, like now, they completely cancel each other out before heading in their opposite directions. Here we have a standing wave. Now, in a standing wave, the wave hits a barrier and then reflects back. And as it interferes with itself, it creates a wave that looks like it's just bouncing up and down without really moving. That's what we call a standing wave. In reality, it's two waves with the same frequency and amplitude moving past each other in opposite directions. A beat is a phenomenon that happens when two waves interfere with each other that have slightly different frequencies. Because their frequencies are slightly different, they will go from lining up and constructively interfering and then being out of alignment and destructively interfering. So the waves will get slightly louder, if it's sound waves, and then slightly fainter. If you've ever heard musicians tuning up before a performance, what happens is that they're all trying to play the exact same note, and they listen for this beat. If they're slightly out of tune with another musician, then they'll be able to hear this wobbling noise where the combined notes of their instrument and the other instrument get louder than softer, then louder than softer. And the rate at which that wobble happens can tell them how far they are out of tune with the other musician. So they can tune their instruments until they can play the notes together and no longer hear that wobble, and that lets them know that they're perfectly in tune with each other. The last thing we're going to talk about in this lesson is the Doppler effect. Now, the Doppler effect is an apparent change in frequency whenever a source of sound is moving or when you are moving with respect to a source of sound. Say, for example, there's an ambulance driving down the road with its siren blaring. If you are in the direction that the ambulance is moving, in other words, you're standing over here and the ambulance is moving towards you, not directly towards you, of course, you're not standing right in the middle of the road, but just on the sidewalk, then the sound waves from the siren will get bunched up as the ambulance moves towards you, and you will hear a slightly higher frequency. As the ambulance rushes past you, then the sound waves will be getting stretched out, and you will hear a lower frequency. So I've linked to a website that will sort of illustrate that. I'm going to pause for just a moment, and when I unpause, I will be on that website and ready to show you a demonstration, and that will end our lesson. Okay, in this animation, when I click the play button, this red object here will start moving and emitting sound waves. And just to sort of show you, the speed of the sound waves is given as 80. The units are arbitrary, which means it's 80, it doesn't matter 80 what, meters per second, miles per hour, it doesn't really matter. That's just the speed of the sound waves. The speed of the source is 50, so it is moving slower than the speed of sound. But it is still moving, so you can see as it moves, the sound waves that it is giving off get bunched up ahead of it, and the sound waves behind it get stretched out. So if you were sitting, say, here where the arrow is, listening, as the object passed you, or as the object approached you, you would hear a higher frequency sound, and then as the object passed you, you would hear a lower frequency. If you've ever heard a car go by, and it goes, okay, that's why that happens. As the car is heading towards you, you hear that, and then it goes by and you hear, the frequency drops. So let's see, as this object passes by, we hear a higher frequency here, and then as it goes by, we hear a lower frequency. Now let's reset the simulation, and we're going to bump up the speed. We're going to increase the speed until it is traveling at 80, which is the same as the speed of sound. So if this were an airplane, it would be traveling at the sound barrier. We call that Mach 1. Now, as it travels, it is keeping up with its own sound waves. So it builds up this high-pressure wall of sound waves. If this object were to travel by you, when this high-pressure sound wave hits you, you would hear it as a sonic boom. It would be a loud boom followed by a very low-pressure sound wave behind it. All right, so this is what happens when an object travels at the speed of sound. It generates a high-pressure wall of sound waves. Now let's ramp up the speed even further. So now the object is traveling supersonic, that is faster than the speed of sound. And as it does, it leaves its own sound waves behind it, and it creates this cone. Again, this is like a shock wave, a high-pressure shock wave of sound. Now, if you're sitting right here where my arrow is, you would not even hear the object yet because its sound waves have not reached you. You would not hear it until until the object got so that you were here, and then this cone of sound hits you, and you would hear all that sound at once as a tremendous bang. And again, that's what causes a sonic boom. When an object travels faster than the speed of sound, the sound waves that it creates get all bunched up, and you hear them all at once. So folks, that is truly going to be the end of the lesson for today. I appreciate your time and attention, and I know it was a little bit longer than usual. Head on over to Google Classroom, please, and there will be an assignment there for you to do. In the meantime, or excuse me, tomorrow, please come and check back. We'll go into our next lesson, which is going to be about electromagnetic waves, which includes light. I look forward to seeing you then. Until then, take care. Keep washing your hands. Stay safe. See you tomorrow. Bye.